Hi again. This is the third in a series of videos in February 2023. So in this video, I'm going to show you how to make analysis. So the first two videos were about manipulating and understanding the interface of Dragonfly, manipulating images. The second was on segmentation a little bit, basic segmentation tools. And now we will do not only segmentation, but take it to the next step for some analysis. We're going to import an object which I've prepared. This is within the data that you have associated to this training. We're going to use a concrete sample which has been down sampled. It's quite a small data set for training, easy to use, easy to manipulate, easy to work with. So I'm not going to explain the rendering options. You can do this yourself. As we've done before, this probably will make a little bit of a dark image. Drag that to the left. There we go. That's what the concrete sample looks like. And there are some pores inside. So if we make it with some transparency, we should see that there are air bubbles inside. You can see that on the 2D views, as you see there. Let's focus in this view here. We want to make an analysis. So how do we do that? We need to make a segmentation first of all. We're going to use define range here. We're going to use lower O2 for this. So add to new and untick the define range button. So now we have a region of interest with all air outside and inside. So how do we remove outside air? Right click, refine region of interest, process islands, remove by largest. So one largest ROI is removed. Then we have all internal pores. So we can even call this pores ROI. And now we also have, in some of these cases, little small individual pixels, which are probably due to noise. So a good approach to use, good practice, is to refine process islands, remove by voxel count. So this means anything, if we put in here 27, it means for something to be seen as a pore, it should have at least 27 voxels, which means for a spherical, almost spherical object, 3 by 3 by 3 in 3 axes, which is 27. So less than 3 pixels in any one axis is not considered a pore. So those are removed, and now we have a pores ROI. Now to make a detailed analysis of that, we need each pore to be seen as a separate entity in a multi-ROI. So right-click on the region of interest, go to connected components, new multi-ROI. If we make that visible, we can see each pore has a different color already. You can actually already visualize that if you're interested to do that. It's actually looking quite nice for this kind of data. But the color coding here means nothing. It just means each object has a separate, each pore has a separate value. Has a separate, is a separate object. It's not having any values yet. So if we right click on this multi-ROI, we can use scalar generator, which is the function to calculate values. We go to basic measurements. We can use volume, equivalent spherical diameter. There are many others. Sphericity is probably the most important, and maybe distance to closest object. So we can compute those four. The distance to closest object is the one which takes a bit of time in this case, but it's quite useful because it will show you that which pores are further apart from others, and the opposite way is actually important. When pores are very close together, these can sometimes be considered as one and is something which can be used in a non-destructive testing evaluation. So let's just wait for that computation. If you have a big data set, I would recommend just using volume and equivalent spherical diameter and maybe sphericity. Those are quite fast calculations, actually. But once we have calculated this, we will be able to visualize according to each of those parameters in 3D and in 2D, and also make statistical analysis inside Dragonfly and export all data to CSV files. And as a final step, after we've done all of that, I will explain to you a little bit why one pore there is not included in the analysis. So the computation is done. What we do is we close scalar generator at this point. Still nothing is shown because it doesn't know what you want to see. So on the multi-ROI, when it's selected on the measurement here, we can select volume and it would color code by volume. So the yellow is the biggest one by volume. We can sort by equivalent spherical diameter. The biggest one is still the same one, which is the largest diameter. Sphericity is a bit different because the smaller pores are more spherical. And then there's distance to closest object, where the yellow one is the one that is furthest away from all other pores. Its nearest pore is 4.3 millimeters away. So these are some of the analysis tools that can be used. If we just focus on equivalent spherical diameter, we can click on this button here to make a statistical analysis of that. Or actually, in this case, it would be actually interesting to look at sphericity. There we see a sphericity distribution, and you can change it here, what you want to look at. You can save, you can make, for example, only 40 bins, and if you like that, and export that to CSV or save it to a figure file. So you can also, that's for saving the statistical, the histogram. For saving all the data, you can click on this button to export to a CSV file, export all slots, or just volume and sphericity, or whatever you want. So you can export that to all to a CSV file. So each pore has its own data in the CSV file. So that's basically the process. What I wanted to show you is this pore here. And there you can see why it's not included in the analysis. It's an open pore connected to the surface. So I can spend a bit of time showing you how to include that in the analysis. Let's do that real briefly. There's different ways of doing it. The simplest way is to use upper Otsu to define the material, and then we can check what is the size of this cavity. It's approximately 0.7 millimeters opening. So what we can do is we can, on this region of interest, go to refine process island, refine fill connected pores with diameter smaller than 0.7 millimeters. And be careful of point and comma. It takes the default of your Windows system. So if it does not work at this point, you should use comma. My system is for decimal optimized. So the new region of interest now has that cavity closed, but then we still need to close up fill inner areas 3D. And now we have the full object. It's also filled some areas on the surface. So if you compare this to the original, there's some, if you show both, there's some stuff on the surface. So what I would do is I would take the new one, which is closed, and I would do an erode function just to get rid of surface pixels like that, even possibly twice. And then what I would do is I would say, let's put off all of this so that we don't get confused. This is now, this is full closed cube. Let's do that. We can now also do a lower Otsu of add to new and put that off. So this is all air. So if we take the full closed cube and all air, this is the intersection. If you click on one and hold down Control and click on the other, you can create an intersection ROI of those. So if you click on intersect, you now have all pores which are open and closed. And then you can again do the refine ROI to get rid of the smallest ones. And then we have open and closed pores included. Okay, that's all for this video. You don't need to do this last step. Just simply make a define range and make an analysis of the porosity. All right. See you in the next video.